Hello, everyone, and welcome back to the Virtual Eclipse Community Meetup. I'm your host, Stephanie Swart, and today I'm joined by Dan Heidinga from IBM.
Excited today to talk about OpenJ9. And so without further ado, let me pull up my slides. And okay. So I'm Dan Heidinga. I've worked with IBM for over 10 years now, and I'm super excited to get to talk to you today about Eclipse OpenJ9, Eclipse's own JVM. I've been involved in this technology for over 10 years now, and so I'm really excited to get to share it with the world, to get to see the kinds of things other people are going to be able to do with the tech and to grow the community. So let's jump in and learn a little bit more about OpenJ9. So this is my standard safe harbor slide. This is shows that I work for a company with a lot of lawyers, and basically it means don't make any product decisions based off what I'm going to be telling you today. All right, so OpenJ9. So Eclipse OpenJ9 was created in September of 2017, which is just over half a year old at this point. The really cool thing about the Eclipse OpenJ9 though is that the project has been around, the code base has been around for a great deal, many more years than that. It actually has a pedigree going back prior to Java 1.4, and even parts of the code base can trace their way all the way back to Object Technology International's Smalltalk VM. So there's a lot of man-years of effort and energy that have gone into creating the Eclipse OpenJ9 JVM. If you're interested, check out the GitHub or the website for more details on the project. One of our claims to fame, though, is our licensing, and that's that we're, I believe, the second project to be licensed under the new Apache Public License v2. Sorry, the new Eclipse Public License v2. We're dual licensed under both that and Apache. But for those who may not be aware, the EPL v2 license is really cool in that it's got a secondary licenses clause, which means it's possible to combine with GPL v2 class path accepted code. This is really important because it allows combining the OpenJ9 JVM with the class libraries from OpenJDK. Being an Eclipse project, of course, we're always looking to build and grow our community. If you're interested in contributing or interested in JVM development, or you have experience reports on using OpenJ9, we'd love to hear that. Come join our project. Come communicate with us at GitHub or through Slack. I'll put up links to those later. But like any Eclipse community, we're really looking to grow that to get as much of the user community involved as we can. And we're all very happy with the way that Eclipse runs communities, that they are open to everybody to contribute. So for the adventurous of you, you can compile OpenJ9 yourself. But if you're just interested in getting a binary to kick the tires a bit, you're also welcome to grab a binary from the Adopt OpenJDK project. This was a project created by the London Java user community. They looked at OpenJDK and said, it's kind of hard to build OpenJDK. It's kind of hard to validate that it's working, and to make sure that you're running exactly the right patch levels at any given time. And it's also hard to be getting JCK binaries. So they said nobody doing JVMs is really competing on the build farm. The areas that they want to be competing on is the innovation they're adding to their JVM. And so they said, let's create a common infrastructure that anybody who wants to build JVMs can use that to be able to do this. So this is a great place to go get your OpenJDK binaries, and in particular, at least from my point of view, it's a great place to go get binaries for OpenJ9. I mentioned earlier that Adopt runs JCKs on their binaries, and OpenJ9 also has the claim to fame of being the first release there that has been JCK certified at Adopt. So the OpenJ9 Java 8 binaries corresponding to the last OpenJDK Java 8 patch level are JCK certified. So grab those and feel free to run them in production. Also, the Adopt community puts up Docker images. So if you're more of a Docker person, feel free to grab the images from here and check out the OpenJ9 ones in particular. So that gives us an intro to the project and where to get binaries. But what exactly is a JVM? So OpenJ9 is a JVM. It's not a full JDK. So what's the relationship between these two things? Well, going back to our standard English classes and these kind of analogy questions, a JVM is to a JDK as blank is to a car. And so a JVM is the engine of the JDK. A JVM is the piece of it that's responsible for running your application. The rest of the JDK provides tools, it provides class libraries, it provides a lot of things that you need to be able to run your application, but it's not responsible for running the actual bytecodes and interpreting your classes. So the engine of the JVM is your interpreter, it's your JIT compiler, which executes your code to make it go faster. It's your garbage collectors that manage your memory, class loaders, verifiers, and then a bunch of tools around reliability, serviceability, accessibility, things to make it so you can understand what your application is doing. But no engine on its own, even one that's had many, many years of incredibly smart people working on it, is complete. You still need the rest of the car. And so we get that from OpenJDK. Now you're probably saying, but OpenJDK already has a JVM. Why do we need a second one? Is it really required to have multiple open source JVMs? And my answer to this, of course, is yes, partly because I'm involved in OpenJ9, and so I'd like to see as many people be able to take it and use it as possible. But also because competition is healthy. If we look back at the history of Java, we see that the competition has been a major driving factor in the evolution of Java. Looking back many years, we see that there were the benchmark wars where every JVM vendor was competing to have the fastest possible implementation. And along the way, caring about footprint, caring about reliability, caring about adding new features, everybody competing and trying to innovate in the JVM. And this has given us a lot of really cool new features, things like compressed references for dealing with applications running on 64-bit that don't need the full address space. It's given us serviceability tooling. It's given us performance, of course. But as an end user, what you really want is all of that under a consistent application API layer, i.e. the Java class libraries, right? You really want to be able to take any JVM and run your application on it and get the same good performance. And so that's what we've been doing. We've taken our JVM, which we've worked very hard over many years, open sourced it at OpenJ9, and then we combine it with OpenJDK. So there's a bunch of work that needs to go into making that happen. So let's walk through a little bit of how the two of these projects relate together. So we start by looking at the two projects separately. Here we see there's OpenJDK. It includes a JVM hotspot already, and then we have the OpenJ9 JVM as well. So to build OpenJ9, what we do is we take the OpenJDK code, we clone it into a Git mirror, and then we remove hotspot out of that mirror. The reason for doing this is we need to place a temporary staging ground for some of the changes that we have to make. And so by giving ourselves a Git mirror, we give ourselves a location to make those changes, a place to hold those patches until we're able to get them upstreamed into OpenJDK. And we remove hotspot because we don't need it as we're going to add our own JVM. Now, we can't just drop OpenJ9 in and be done. There's a bunch of integration work that needs to happen. OpenJDK's makefiles need to be adjusted to be able to work with OpenJ9, to be able to build OpenJ9. There's some patches to the class library code to be able to work with some of the features of OpenJ9, like shared classes, some other minor patches as well, and just places where the interfaces between Hotspot and J9 are slightly different, and we need to be adding extra code to paper over those. But none of this code is where the innovation is happening, and the goal is always to keep this minimal and to upstream it into OpenJDK. We want to be doing the innovation in the JVM at OpenJ9. And so then we take these things and we put them together, and you run a build. For those who've been building OpenJDK, the build process is very similar. It would not be surprising to you at all. The commands are basically clone the repo, run configure, and then run make images, and away you go. I should give a shout out at this point, though, to another Eclipse project, and that's the Eclipse OMR project. So OpenJ9, the JVM, is composed of actually two Eclipse projects. It's got OpenJ9 and OMR. Both of them have the same code base pedigree. They both go back many, many years. And OMR was open sourced a few years, probably 1 year before OpenJ9. And the reason for that is we looked at the technology we had and we said, there's a lot of really amazing technology here that isn't Java specific. There's layers to make it easy to port from operating system to be able to work with different threading APIs, whether that's Win32 or POSIX on Linux-based systems. And then there's just-in-time compilers and garbage collectors, which are sort of the headline features. But a lot of that code isn't Java-specific. There are Java-specific additions to that code, but you really could take it and run and build any language you wanted. And so we really see these as two separate projects. And we've been able to take OMR and do prototypes of other languages, adjusting it into Swift, into JavaScript VMs, into Ruby, into Python. And so there's a lot of really cool technology there. So just a shout out to the OMR project, that if you're involved or interested in language development, please check that out as well. Okay. With OpenJ9 though, we've taken a slightly different approach to how we're going to build and manage our source code than what we see at the OpenJDK project. So OpenJDK typically creates a new set of repos for each release. So there's a set of repos for JDK 8, there's a set for 9, there's another set for 10, and now they've created a JDK head stream that they'll split new releases from. So this model works quite well for them, but we said because we're combining a JVM into each of these, we don't want to have separate streams for every Java release. We really want to have one stream, one place to be able to innovate so that every Java version can get that benefit. We won't be able to backport the sort of headline features of any given JDK release, the ones that are part of the platform spec, but we will be able to take all the other innovation, the performance improvements, the footprint improvements, better container support, better performance, whatever it may be, and enable that on whatever level of Java you're running on. This is particularly important these days with the changes to the release cadence at OpenJDK. For those that aren't aware, OpenJDK has moved to a 6-month release cycle where there are only some of those releases that are long-term supported. In order to be able to make OpenJ9 work with all of them, we don't want to be maintaining that many versions of our code base. So we decided that we would try and do this in one source stream, and so far it's been working quite well. So, and it's going to be a benefit to everybody using OpenJ9, as even those who are on 8 get new features and more performance. Okay, so we're going to switch gears a little bit. We've talked about intro of the OpenJ9 project. We've talked about how it fits with OpenJDK. And then the other thing I promised to do in this talk was to talk about how OpenJ9 is particularly useful in cloud environments, and to intro some of the really cool features we've put into those environments. So before I do that, though, I should highlight, what are the requirements of cloud runtimes? A lot of those are small footprint. in a cloud environment, you typically pay for the amount of memory that you're using more than you pay for the amount of compute. So memory is often the biggest cost in what you're trying to run. For cloud providers, the more memory your application uses, the fewer of them you can pack onto a machine, so it raises their operating costs. For cloud users, the smaller your runtime is, the more of them you can run, and the less you're paying because you're getting charged at gigabits per hour. And then in cloud environments, another really important feature is fast startup. Right? We're seeing fewer large monoliths deployed and more microservices. We're seeing more horizontal scaling, and so you want to be able to delay that scale out as long as possible. And then once you do scale, you want a fast startup, because every time you scale out, you're paying for more memory again. And then every one of those scaled instances, you want them to get up to speed as quickly as possible, because again, gigabits per hour is the key metric, right? You're being charged by how much memory you're using and how long you're using it. Okay, so those are the kinds of requirements that are really important in the cloud. How does OpenJ9 address some of those? So I'd like to start by showing just a footprint demo using a couple of Docker images. I'm going to start by just showing what the Docker image, the Docker file looks like. So here's our Docker file. It's basically saying, go get a build of OpenJ9, set up to be able to run Spring's pet clinic application, and then the last line here is just the command that we're going to run, right? Java-jar Spring pet clinic. And up here in this top window, I'm running Docker stats, so we can see how much memory each Docker container is using. So I'm going to run this. And we'll watch what the stats are. Above, we see the amount of memory being used as Pet Clinic is getting up and running. This is just a standard Spring demo application, and it nicely prints for us the startup time. So we see that Pet Clinic took just over 9 seconds to get up and running. And we see that when running on OpenJ9, we're using 160 meg, so a reasonable footprint. Now we're going to run the same application on OpenJDK as well. And just to show that I'm using the same Docker files, here's the OpenJDK version. It's basically the same thing. It's just pulling a different OpenJDK binary, one that has hotspot in it instead of J9. And we'll just diff the two of them. Right, the only difference between the two of them is where we're pulling from. Right, I will launch this one as well. And we will watch the memory usage of it. So again, it's running the exact same application, and we're getting up and running. Here we see OpenJDK started in 9.95 seconds, but it's using 480 meg. So almost 3 times the amount of memory that OpenJ9 is using. Right, so let's look at those startup times. OpenJDK took 9.995 seconds. OpenJ9 took just over 9 seconds. So you're getting about the same startup time, but you're getting a significantly smaller footprint from OpenJ9. So now I'm just going to take these 2 containers down for a minute. And then we'll switch back to the slides again. So that's the base install of OpenJ9 takes about 3 times less memory. But OpenJ9 has some features that lets it do even better than that, and even better for startup than that. So I've given other talks where I've talked about why the class file format for the JDK is not a great format for a JVM to interpret and to run with. And so in OpenJ9, we looked at our Smalltalk heritage actually and said that kind of symbolic data doesn't need to be in RAM. In our old Smalltalk days, in our embedded environments, and even some of our J2ME days, we were able to take that data and put it into ROM and actually flash it into ROM so that you didn't pay for you didn't waste the small amount of RAM that you had at runtime on symbolic data that was never going to change. So we take the class file and we convert it into a ROM class, which throws away the data that we don't need. There's a lot of data in a class file that's somewhat redundant, and so we get rid of that. And then we also were careful in how we design the format, and we set some design goals. And some of those design goals are that it's truly treated like ROM. So once it gets initialized the first time, it's never touched again. So you can create a ROM class and nobody will ever write to it again. And then we made sure that it was position independent. So you can take a ROM class and you can move it around in the address space without any problems. Now, a JVM, when it's executing, doesn't just use the symbolic data. It has to be able to do a bunch of lookups. Like when you go to invoke a method, it needs to go find the method it's actually invoking. It needs to find the vtable slot, so a bunch of data, and it needs to be able to save that data somewhere. So we have a RAM class as well, and that RAM class is basically a cache for the data that we look up at runtime. So we have the ROM class, which is smaller than a class file. It's never written to once it's been created, and it's position independent. And then we have a RAM class, which carries the live data for a particular class. Now, if we take multiple JVMs and we're running them on the same system, maybe we've taken our service and we're scaling it out horizontally. Maybe we've just decided we're going to run 3 versions of this, or maybe we're running 3 versions of our IDE on our desktop and we really want to be able to save memory. And so if we look at what we're running, we've got the JVM, each one running the same thing, and they've loaded basically the same classes. So everybody's got a copy of object, everybody's got a copy of string, everybody's got the rest of the class libraries, the jar files that you're using in your application, and then whatever other code you've written. And each one of them at startup has to load those classes. And that's often a major part of the startup cost, is doing class loading. So we looked at these and we said, wait a minute, why are we converting these class files into ROM classes, getting the exact same thing, and then never writing to it again? Why are we doing this in each JVM, right? We have these things that are all the same. Maybe we can do something to share them, right? This is really the model that static languages like C and C++ take, right? Your code in those languages gets loaded in DLLs or shared libraries typically, and no matter how many times you run that application, you share that same code. So we said, how do we do this in a JVM? So we created a shared memory area that we're able to store the ROM classes into. And the first time that we create a class, we store it away into the shared classes cache so that the next run or other JVMs are able to reuse that ROM class. Now, there's a bunch of heuristics built into the JVM to make sure that we don't give you back the wrong class, that we only give you back the ROM class for the class file that you currently have. And if ever those heuristics fail, we will actually fall back to a comparison to make sure that you're using exactly the same thing. Now, this has a couple of benefits, particularly when you're running multiple JVMs on the same machine. You get a slight startup performance improvement, and you usually get about a 20% footprint improvement just from using shared classes cache and caching these ROM classes. Now, being the JVM engineers that we are, we looked at this and said, now that I've got this shared area where I can stash information and reuse it, I'd really like to be able to do other things with that as well. So OpenJ9 introduced dynamic AOT. So what is AOT? Well, AOT is ahead of time compiled code. This is in comparison to, or in contrast to, the just-in-time compiled code that we're used to running when we run Java, right? So we run Java, we get our application up and running, the JIT compiler kicks in, it compiles code and makes your application go faster. Ahead of time compiled code is typically done ahead of time and stored somewhere to be run. Now, true ahead of time compiled code doesn't have any profile data to guide it. It's not specific to the application you're running, and so it has to do a lot of checks and things that we really don't want to do that punish your application performance, both in terms of startup and throughput. So what we looked at was instead allowing the JIT compiler as it runs to be able to generate this code, this AOT code, and save it away for the next run. So it generates the code, it generates some profiling data and some hints to the JIT and saves them away into the shared classes cache. So this code is ready to run for the next time you want to run your application. And this often gives a startup improvement of around 10 to 30%. The tagline for this being compile once, run manywhere. Again, this is a dynamic library created at runtime. So, but this really does bring in a distinction between two types of runs: those that are cold, so the first runs that generate the AOT code, and the warm runs, or the ones that benefit from the AOT code that has been generated already. So what do you get with this AOT code? Well, we're not able to run it directly out of the shared classes cache. We take the code and we actually have to copy it into the runtime that you're running. It needs to be relocatable then, because we need to patch certain places in that code to refer to the J9 RAM classes or the live classes in your application. But even with that relocation, the AOT loads are hundreds of times faster than doing the compilation. So you're still getting all of the benefits of very fast startup. It does come at a slight cost in that the code has to be slightly more generic to be able to be reused in different contexts. So you trade off a slight amount of optimization here to get your faster startup. But because we've saved away the profile data as well, we're able to then recompile that code and continue to drive towards peak performance. So that's what shared classes gives you by default. We have a couple of other options that are good for tuning in this kind of environment as well. And so one of those is X Quick Start, which is designed to give you the fastest startup possible for short-lived tasks. This is really good for when you're running small scripts or small apps on your own desktop or anything else that's very short-lived. You're going to trade off your peak throughput, but your theoretical peak throughput, if your application wasn't going to stay up long enough, then it doesn't really matter because you wouldn't have gotten to that peak throughput anyways. And then we also have Xtune Virtualized, which is for tuning containers. And the idea is it's got some heuristics based on the amount of CPU that the JVM will consume and the amount of memory footprint that will consume to be able to ensure that running multiple things inside those containers or inside your virtualized environment, the JVM is playing nicely with the other applications. This does have an effect on throughput. It usually lowers the max throughput by less than 5%, but you get a big improvement in startup and ramp up. So I'd like to do a demo now of the shared classes cache. We're going to go look at our pet clinic application again. So here I'm going to use almost the exact same Docker file. This time I'm going to use one that enables the shared classes cache. So here, what I've added to my Docker file is a couple of command line options. I'm using the X Quick Start option I mentioned. I've enabled shared classes, and I've used this -x SCM X command to say that use a 50 meg shared classes cache. This is just sort of a random number I've picked to give us a value. You can tune this for your application as well, but 50 megs usually works fairly well. All right, so I'm going to start this application now. Making sure that I typed the command line correctly. Docker run --rm--it demo OpenJ9.cold. And so this is the cold run I mentioned earlier in the talk about shared classes cache, right? I don't have a cache yet. This particular run, I'm creating my cache, and I'm filling it with the classes as Spring's pet clinic gets up and running. And so we see that this took slightly longer to run because it has to fill that cache. It's doing those AOT compiles. It's saving away the ROM classes. So that cold run has a slight hit to it, but we still see that it's using about the same amount of memory as it was before. But now I'm going to take that container and I'm going to save it. So I'm going to do Docker commit, and I'm going to take the container ID, and I'm going to commit this as demo.openj9.warm. So I've done my cold run where I've populated the cache. We took 11 seconds to start, and now I'm going to save that away, and then we're going to try rerunning that and see what the difference is in startup time. So I'm going to take this one down for a minute. And then here, instead of running the cold version, I'm going to run the warm version. Let's watch the memory usage and how long it takes to get up and running now that we're using shared classes cache and AOT. So we went from about 11 seconds to get started to now 7.5 seconds. So a fairly significant startup improvement, and we're using about the same amount of memory, which is a pretty good place to be in. So, all right, I'm going to switch back to the slides now. And let's take a look at just a summary of some of those results. Here we're seeing that OpenJ9 and OpenJDK start up in similar amounts of time, just out of the box. But when we enable the shared classes cache and X quick start, we get about a 30% startup win with OpenJ9. That's what I had demoed with the shared classes cache. And then we see that the footprint on OpenJ9 just out of the box is about 60% smaller. So right out of the box, just using OpenJ9 is going to save you, likely 2/3 of the memory, which is a very important, at least on this particular pet clinic application and likely other similar applications, which is a pretty significant savings in cloud environments. And then I don't have a demo for it, but I just wanted to show some of the Xtune virtualized and AOT for ramping up in CPU-constrained environments. And so I've got 3 lines on this screen. The first one we'll look at is the red line, which is using OpenJDK 9, running with hotspot. Getting up to speed and up to peak performance takes a certain amount of time, but the peak is about the same. And then if we look just at base OpenJ9, we're able to get to that peak performance faster. But even faster, though, is if we look at this green line, which is using AOT and Xtune virtualized. So we get to your peak, or the peak performance it's able to get to very quickly, but it's not able to get to the same peak. This is why we often talk about using it in CPU-constrained environments, because in those cases, you're probably willing to get that fast startup and that trade-off of pure throughput. Or for short-lived applications where getting up and running that quickly matters more than the peak theoretical throughput. So at this point, if you're interested in checking out OpenJ9, I'd like to point you at the adopt binaries. Download the binaries, try it out. run your favorite Java application. Let us know how it went. We'd love to hear your experience, whether it's positive and it's how great this has worked for you, or even if there's been a problem along the way. We'd love to hear that too and help you work through that and tune your way through that. Check out our GitHub project as well if you're interested in either reporting issues or providing feedback. It's a great way to do that. Or check out the code and come hack with us on the amazing JVM that is OpenJ9. We're also on Slack as well, so we'd love to have you join us and chat with us there. At this point, thank you to everybody for letting me come to talk with you today about OpenJ9. So.
Absolutely. Thank you so much, Dan, for such a wonderful presentation. And of course, thank you for for tuning in to our community. So we actually do have a couple questions coming from our YouTube channel. The first one is, does OpenJ9 do a 6-month release cycle, or will it follow the Eclipse standard release cycle once a year?
We're primarily going to focus on the long-term support releases. So the long-term support releases are the Java 8, Java 11, and I think Java 17 after that. But we'd like to be trying to track OpenJDK and releasing very quickly after each new JDK level.
Awesome. And the next question is, will the Eclipse IDE come with OpenJ9 as a bundled JRE?
That's a great question. We'd love to be able to have OpenJ9 shipping as the default JRE for Eclipse IDE. It's something we haven't been pursuing yet, but we should be working on, especially now that we've recently had Windows binaries released at Adopt. So there should now be OpenJ9 Windows binaries that you can use.
Awesome. And it looks like we have one more question. So how the GC works on OpenJ9?
How does the GC work on OpenJ9? That's a great question, and a longer answer that I'd have to give. OpenJ9 has several different GC policies. The default policy is generational concurrent, so it's a standard scavenger and stop the world old gen collector. There's also a balance collector, which is similar to OpenJDK's G1 collector. We also have two other policies, opt throughput and opt average pause, which are for peak throughput or trying to get smaller pauses. And then we also have a soft real-time collector called metronome. I'd love to go into more details on that, but that's probably longer than we have time for today.
And it looks like we have no further questions, so we'll be monitoring our channels, the YouTube chat section, the Twitter feed, the Meetup page. So if anybody has any other questions, feel free to drop your questions on any of those channels and we will answer them. We'll send them over to Dan to answer. So again, I'd like to say thank you to Daniel for presenting. It was a fantastic demo and presentation. And thank you for tuning in, community. We will see you next time.
Thanks, everyone.